Hello everyone, welcome to ML Summer School's module on sequential learning. I am Arvind, an applied scientist in Alexa and LU team. In this lecture, I will discuss about hidden Markov models in sequential learning topic. This is the outline of my presentation. First, I will start with introduction to HMM, and then I will discuss about three different problems mainly addressed in HMM. One is inference, likelihood computation, and training to learn the parameters of HMM. Let's consider parts of speech tagging problem as an example sequential learning problem. In this particular task, the objective is to classify the words into different categories as nouns, verbs, adjectives, etc. The main challenge involved in this task is that given the words are ambiguous, that is, words can have one or more speech tags. Let's consider an example. I like to play cricket. In this particular example sentence, play is a verb, while if you consider the example sentence, I would like to act in that play. Play is a noun. So we require sequence information to disambiguate. So this comes under a sequential learning problem. In general framework, given is input sequence, the goal is to predict the corresponding label sequence. For part of speech tagging problem, input sequence is X and parts of speech tags are indicated using Y's. These are modeled using two different approaches. One is generative approach, where we model the joint distribution between the words and the POS labels, which is P of X comma Y. In the discriminative approach, we model the conditional distribution P of Y given X. In this presentation, we are discussing about the generative approach, and we can go into more details on how to model joint distribution using HMMs. Let's define some notation here. Given the training examples, X input observations X and Y's are the labels, where K indicates the sequence length, and the objective is to model this using a joint distribution P of X comma Y. Once we obtain the joint distribution, we can find the Y estimate Y hat by computing the argmax for the joint probability distribution. This is the graphical view of HMM. For the example sentence, the dog barked. This is generated by the underlying hidden state sequence Y1, Y2, Y3. These are directly these underlying hidden states can be directly mapped to the word labels. The main challenge here is we know the observation sequence, but we don't know the hidden states which generated this sequence. So during the inference problem, we have to estimate the most probable state sequence given the input sequence. In this example, the dog barks. The corresponding POS label sequence is Y1 equal to determiner for the word the, and Y2 equal to noun for the word dog, and Y3 equal to verb for the word barks. Let's discuss on how to generate a sentence using HMM. From the start state, we can visit any of the other states. Either it can be determiner or noun or verb, and emit the observation word, the dog or barks in the vocabulary, and then transition to the other state, either noun or verb, or do a self transition from the same state, self transition to the same state. This is how we can generate a sentence using HMM in a generative way. Let's establish some notation. Let's say V is the set of all words in the language. In general, this will be in the order of millions, and S be the set of all states or tags, and S can be determiner, noun, verb, and all possible POS tags, and much more fine-grained categories can also come in. And let X be the sentence in the language, and X1, X2, X3, X4 up to so on. Xn represents the words, and Y represent the states of the labels. Let's consider a simple example, the dog barks, and let's see what are the parameters involved in modeling using HMM. These are the values which we had provided as a sake of example for understanding. From the start state, let's say in the start state, we can visit any of the three states: determiner, a noun, or a verb. So the initial transition probability is captured by initial probabilities, which is denoted as a pi. And after reaching to any of these states, we can transition to other state, noun or a verb. These are captured using transition probabilities a yt minus 1 comma yt, where rows indicate where this rows indicates the previous state yt minus 1, and the columns indicates the current state yt. For this example, a det comma noun indicates the transitioning from determiner state to noun state, which is indicated here, and transitioning from noun to verb is indicated here. And after reaching a state, HMM emits a observation word, which comes from which emits out of the vocabulary which we consider. In this particular, the vocabulary is the dog barks. So the probability of emitting the word the in the determiner state is given by 0.04, which is indicated here, and the probability of emitting the word barks from the noun state is 0.031, which is indicated here. So these are the parameters involved in HMM. Let's define it more formally. The initial probability of starting from a state Si is indicated using pi Si, and the transition probabilities, probability of transitioning from state SL to state SM is indicated by ASL SM, and the probability of emitting a word Vk at state Sj is indicated by B Sj comma Vi. Sorry, this is a typo here. This is Vk. In hidden Markov models, we want to model the joint distribution of observation and the hidden state sequence. So we can express this joint distribution in terms of initial probabilities and the transition probabilities. The factorization for this factorization, we made two assumptions. One is the Markovian process. A state is conditionally independent of all other states given the previous state, which means that probability of yt given yt minus 1 is conditionally independent of all other previous states. And one more assumption is observation independence. The output observation xt depends only on the state that produces the observation, which is indicated by probability of xt given yt. Given the yt, the xt is conditionally independent of all the previous observation yt, all the previous states yt minus 1 to y1, and all the previous observation xt minus x1. So this is observation independence. Since in HMM we only know the observation sequence and the underlying hidden state sequence is unknown, we have to in order to compute the likelihood over the data, we have to summate over all possible hidden state sequences. So this is obtained by marginalizing over the state sequence. With this background on the HMM, let's see the three problems we want to address in HMMs. First one is the inference problem. Given an observation sequence and an HMM, determine the most possible hidden state sequence. And in the likelihood problem, determine the overall likelihood of an observation sequence X being generated by the HMM. While in the training, we have to find the best parameters for HMM for the given data. Let's first discuss about the inference problem. Let's understand the inference problem using the POS sequential learning problem and consider the example, the dog barks. Given this sequence, we have to find the underlying hidden state sequence which generated this sequence. This is the tree list diagram of HMM where the states are indicated here. And while going from left to right, this indicates the instance of sequence 1, 2, and 3. For the given sentence dog barks, we have to find the best possible sequence state it generated. To do it efficiently in HMMs, we have to do this one efficiently in the HMMs. If we do in a brute force way, there are like 27 possible sequences paths are possible. Since there are 3 states and the sequence length is n, there are 27 possible possible paths are possible. So in order to do it efficiently, what we use in HM is the Viterbi decoding, which is popularly known as a dynamic programming. So in order to compute, in order to perform the inference, first let's define deltas here. The initial delta S of 1 is the probability of starting in the state S and emitting the symbol x1 in the first position. This is indicated by this is computed by initial probability and emission probability of being in a state S and emitting the word x1. So this is how the deltas are computed in the first instance, and in the subsequent instances, we can make use of recursive solution to compute this. This is possible because of the Markovian assumption we made, where the current state is independent only on the previous state, and the current state is dependent only on the previous state and independent on all the previous other states. So by making use of the Markovian assumption, we can rewrite deltas in terms of previous deltas and the transition probabilities from that particular state to the current state, and also the emission probability of being in the state SM and emitting the symbol XT. And in order to decode the sequence, best possible sequence, similar to the backtracking pointer in dynamic programming, here we use sigma to backtrack the best possible state sequence, which is the argmax or SL, which keeps track of what is the best possible previous state. Let's try to understand this with an example. Let's try to decode the hidden state for the example which we considered, the dog barks. Let's say if you want to compute delta for the delta 2 at the second sequence instance, and for the word dog, delta noun of 2, which is indicated by delta noun of 2, represents the probability of reaching the state noun and emitting the symbol dog. And we need to find what is the best possible path out of these 3 to reach this particular state. In order to compute that, first let's see the possibility of coming from determiner state and in that state emitting the symbol the. So this is computed by pi det into multiplied by emission probability of the word the being in the state determiner. And in order to compute the path, we have to multiply with the transition probability. After multiplying with the transition probability, and then reaching the state noun and emitting the symbol dog, which is indicated by emission probability of b noun comma dog. This is the first term, and we have to compute all possible paths. So the other possibility is reaching from the state noun to noun by emitting, and while in the previous state emitting the symbol the. So this is represented by this particular term being in the state, the initial probability, the previous delta noun into transition probability and the emission probability here. Similarly, we can uh, compute the path associated with verb to noun using this equation. So out of these three, we have to find the best possible path. So let's consider the previous values and substitute the values here. So these are the values. Recall that the observation, the emission probability of the word the being in the state noun is 0, and also the emission probability of the word the being in the state verb is also 0. So in this expression, these two terms will become 0, and the argmax of the previous term in the back pointing tracking variable will goes to determiner, since the observation probabilities of these two terms are 0. Similarly, we have to compute the deltas for all possible states in all sequences using the recursive approach. And after reaching the final instance of the sequence, we can find the argmax of the deltas which we computed. In this case, it turns out that the last tag, which is the most likely tag, is a verb, and uh, and uh, and after obtaining this, try to find what is the previous best path, and going further backward, we can decode the whole possible state sequence. So this is the inference algorithm in Viterbi. This is similar to what you might have already familiar with the dynamic programming. And the second problem is the likelihood computation problem. Here the goal is to determine the likelihood of the data p theta of x1 given up to so on, given the observation sequence x1 to xn. Since we don't know the likelihood, since we don't have access to the hidden states, we have to marginalize it over all possible hidden state sequence. Summing over all possible state sequence could result in computationally expensive. So let's consider the HMM with n states, and length of observation is t. Let's consider this case. In this case, the possible number of computations involved here is order of t into n power t. By making use of the Markov assumption, we do not have to explicitly compute each possible path, but we can make use of Markovian assumption and then do it efficiently. This one such algorithm is forward algorithm, which results in a reduction in the computational accuracy, which is of order of t n square. Let's see what is forward algorithm. In forward algorithm, the probability of observing the observation sequence x1 to xt and being in the state s at time t is given by alpha s of t, which is the probability of observing the sequence x1 to xt, and the hidden and at the tth instant the hidden state is s. Let's initialize this alphas in the first state as the probability of starting the state sequence with a particular state s is computed as initial probability of being in that state s and emitting the symbol x1. In emitting the symbol x1, probability of emitting the symbol x1 in the state S. This is similar to what we have seen in what we have observed in computing the inference problem using deltas. Similarly, uh, similarly for alpha s sum of t from the initial state to the successive states, we can make use of the recursive solution, recursive approach by the previous alphas and then compute it efficiently rather than enumerating each sequence. Compute the probabilities recursively using the Markovian assumption. That's the idea here. This is mostly similar to the deltas which you computed in inference algorithm, but the only change is that there we use the max operator to obtain the best possible path, while here we perform summation to marginalize over all possible state sequences. And the likelihood of the data is computed by computing the alphas of the final sequence instance and then summing it over all possible states. Similar to the forward probabilities, we can compute the backward probabilities using betas. These are further used in HMM training to find the parameters. To estimate the state occupancy probabilities, betas are utilized over there. We can see it in the later part. So let's try to define the beta and then try to understand how we can also compute the likelihood using beta. The beta indicates the probability of future observations given that HMM is in state S at time t. Similar to forward probabilities, we can also compute backward probabilities starting from the backwards and then coming towards the left side. So we can initialize it with beta s of t, which indicates the final probability, which is equal to 1, and then let's integrate the and then for beta t minus 1 is computed recursively using future betas and the transition probabilities and the observations in the future states. We can also compute likelihood using the backward probabilities using this equation, which is a summation over all possible betas in the initial state and the initial state probability matrix, probability values, and the corresponding emission probabilities. So far we discussed about inference and likelihood problem, and next we will discuss about the training HMM using training HMM parameters and obtain the parameters of the HMM. Based upon the availability of the labeled data, we can train HMM in two approaches. If the entire training data is labeled, then we can perform supervised training. But when the huge amount of data is unlabeled, then we have to go for semi-supervised modeling. Let's first consider the supervised approach. In supervised training, we have access to the labeled data. So the input sequence is associated with the corresponding state sequence. Recall that joint distribution is expressed in the form of Markov in this form by factorizing it in terms of initial probability and transition probabilities and then emission probabilities. We can rewrite this expression since the labeled data is available. We can rewrite this expression in terms of model parameters. If we rewrite this expression, these are the initial probabilities, and p of x given p of y given yt given yt minus 1 is the transition probabilities, which are represented by as. ASL comma SM indicates the state transition from SL to SM, and CA's CA SL comma SM indicates the number of transition from state SL to SM, and BJs are the emission probabilities, and CB indicates the number of emissions of the word VK from the state SJ. So for simplicity, ignore this term and try to estimate the parameters of A's and B's, and by considering this term. Recall that A's and B's are the transition and emission probabilities, and these and this should sum up to 1. So for each SL, the transition probabilities summing over all possible reachable future states should sum up to 1, and similarly within each state, the emission probabilities summation over all possible words should sum up to 1. So these are the constraints used to solve the objective function. So for each state, different different optimization functions are defined for both transition and emission parameters. For transition parameters, this is the objective function, log of the product of the terms involved with transition parameters and the corresponding counts using the constraint over the transition parameters. And similarly for emission parameters, we can define the objective function and the constraint over the over the emission parameters. So these are solved using Lagrange multipliers. So using the Lagrange multipliers, we can introduce the Lagrange variable and then and try to maximize this particular objective function for transition parameters, and the corresponding expression for the emission parameters is this one. So these are the parameters of A's and betas can be obtained by differentiating and equating these objective functions to 0. We can differentiating the terms and equating to 0 will give us this one. In this objective function, we have to differentiate with respect to A, SL, SM, which are the transition parameters which we are interested to estimate. So in this particular summation, there is only one term which will be dependent on ASL, SM. Similarly here, so differentiating with respect to the ASL, SM will result in CA divided by ASL, SM plus this factor. This turns out to be lambda A. So these are the expressions. These are the expressions for the solution for transition and emission parameters, while lambda A and lambda B are the Lagrange multiplier parameters which are unknown. Let's try to estimate these parameters. Rearranging the terms by moving the lambda to RHS and then summing it over all possible states. We know this term is 1, and which implies that lambda equal to summation over SM of the counts of this equation. Similarly, for rearranging the terms and solving for lambda B results in this expression. Once we get the lambdas, we can go back and substitute in this equation to find the transition parameters and beta parameters. So these are the expressions. These are the final estimate of the parameters by solving the Lagrange, by solving the objective function using Lagrange multipliers using the constraints. We arrive at these estimates for transition and emission parameters. Let's understand what this mean in terms of words. So the transition parameters A theta SL, SM indicates the number of transitions from state SL to SM divided by the total number of counts in total number of counts of state SL. Similarly, the probability of emitting a word Vk from state Sj is given by B Sj comma Vk, which are number of emissions from the word Vk from the state Sj, and the number of total counts of state Sj. And these are fairly intuitive. Yeah. These are the solutions we arrive at for supervised learning. Let's see how to do for semi-supervised learning. Let's say some data is labeled. Then we can estimate the initial estimate using the supervised approach, and from the unlabeled data, we can use EM algorithm to estimate the maximum likelihood of unlabeled data by this is an iterative approach. Direct optimization is not possible as the state sequence is hidden, which needs to some overall possible state sequence. And so in order to address this problem, we use EM approach to iteratively estimate the parameters, which maximizes the likelihood of the data. In EM, in order to solve using EM, we have to define an auxiliary function. In this case, it's an expectation over the hidden sequences, hidden state sequences over the joint distribution, where the observations are known and the state sequences are hidden and unknown. In each iteration, we have an expectation step and a maximization step. In expectation step, each step, we compute the expectation over hidden sequences given the current parameter theta I. And once we compute the expectation of this parameter of this expression in the end step, given the current parameter theta I, we need to estimate theta I plus 1 by maximizing the log likelihood, which maximizes this expression. So that is the theta I plus 1 for on every iteration, from iteration to iteration. The likelihood of the data will keep increasing. We'll stop the iterations when the likelihood saturates. So by rewriting the expressions which of the joint distribution in terms of initial probabilities and transition probabilities and emission probabilities, by applying the log, we arrive at this equation. So we also know that expectation is a linear operator. Expectation of sum is equal to sum of expectations. So we can split this expression in terms of in order to compute for each parameter separately, 3 parameters. First one is initial probabilities and the transition probabilities and the emission probabilities. We can compute the 3 objectives separately. So this is the objective function 1, 2, and 3. Let's first consider the objective function 1 and optimize it and find the parameter and find the estimate for initial probabilities. First, we have to compute the expectation over the hidden sequence. So expressing this expectation in terms of summation over the conditional distribution, and writing we can rewrite it in terms of posterior and the model parameters. Let's see how to compute this posterior, and then we'll come back to this particular expression and substitute it. The posterior p theta I of y being in the state s given the observation sequence is proportional to the joint distribution, and we can rearrange the terms here. And then remember, we defined alpha and beta parameters as forward and backward probabilities. So we can make use of the forward and backward probabilities, and then express this term in terms of alphas and betas. This is a remember, this is a proportionality. So in order to, and this is a probability parameter, probability value. So in order to get convert this one into probabilities, we have to normalize with a normalizing constant by summing over all possible state sequence. So once we obtain the posterior, we can go back and substitute it in this expression. In the similar fashion, which we did for supervised learning, the initial parameters are probabilities, and the estimate should sum up to 1. So we introduce the Lagrangian and Lagrangian multiplier, and then rewrite the objective function in this form. We follow the similar steps, differentiating with respect to the parameter we are interested in and equating to 0, and then find the estimate for the Lagrangian, and find the and we can find the estimate for the initial probabilities. So this probability is so initial the estimate is given by alpha 1 of s times beta 1 of s divided by the normalizing constant. What does it mean is, this indicates the expected frequency being of state s at the time t1. Similar approach is carried out for the objective function to estimate the parameters of transition probabilities, computing the conditional expectation and factorizing and computing the conditional expectation and factorizing it in terms of posterior and model parameters. Let's see what the posterior in this case looks like. Similar to what we did earlier, the posterior can be represented in terms of joint distribution, and then factorizing it in terms of forward and backward probabilities. We arrive at this equation, and similarly, if we normalize it, we can go back and substitute this posterior in this expression, and introduce the Lagrangian multiplier, and differentiating and solving it, we get this particular estimate, which indicates that expected number of transitions from state SL to SM divided by expected number of transitions from state SL. This is similar. The solution is similar to the solution we arrived during supervised approach, where we have the number of transitions from state SL to SM. Since the data, in unsupervised learning, we don't have access to the label data, what we observed, what we did here is to estimate it and approximate using the soft labels. That's the difference from supervised to unsupervised approach. Similarly, we can estimate the emission probabilities by solving the objective function 3. We can estimate the emission probabilities in terms of gamma, and I here indicates the indicator variable, indicator function, which takes 1 when the observation xt equal to vk, what vk, where gamma t indicate gamma SL of t is the probability of being in state SL at time t given the entire observation sequence. So in terms of watts, we can express this expression as expected number of times in state SL and observing the symbol Vk divided by expected number of times in state SL. These are the estimates for B in unsupervised learning. Sorry, semi-supervised learning. So far, this is about estimating the parameters in HMM training using supervised and semi-supervised approach. We consider the example of POS problem, parts of speech tagging problem. We can also apply the similar approaches for in speech applications. The same modeling approach holds for application speech like automatic speech recognition and text-to-speech synthesis. The difference is that in pure stacking problem, the observations are are in discrete space, and it is modeled using probability mass function. While in ASR or speech applications, the observations are in continuous space. Let's say given a speech signal, it is first segmented into short windows of duration 20 to 30 milliseconds with an overlap of 10 milliseconds in successive frames and extract spectral features. These are used as a feature sequence x1 to xn. Given an acoustic sequence as an input, the acoustic model is modeled using HMM, and given the acoustic sequence, it estimates the best possible phone sequence. And since the observations are continuous space, unlike in pure stacking problem where we considered probability mass function, in the case of speech applications, we consider emission probabilities as a continuous densities, and this can be modeled using Gaussian mixture models. That's about speech applications. Let's recap what we discussed so far. First, we considered a simple example of using of POS problem, and we formulated it in terms of sequence learning problem and model using HMM. And then we discussed about the problems involved in HMM, inference problem. In inference problem, we used we defined delta parameters, and using dynamic programming, which is also known as Viterbi algorithm, we performed inference efficiently. And also we discussed about forward algorithm to compute the likelihood of the data using forward and backward probabilities. And finally, we discussed two approaches to estimate the parameters when depending upon the availability of the data, labeled data, in supervised and semi-supervised approaches. On a final note, HMMs are classical models which are used to solve the sequence learning problems. Recently, there are more advanced methods using neural network-based approaches to address these sequential learning problems. In the next part of this session, Pritham will cover attention and bed-based models to address the sequential learning problems. Thank you.
Hi everyone, welcome to the second session on sequential learning. I am Preetham Verma. I work as a research scientist in Amazon Alexa team in Bangalore. So let's get started. In terms of the topics that we'll be covering today, we'll be covering four topics. The first topic is attention mechanism in LSTM. The second one is self-attention and transformers. The third topic is subword modeling, GPT, BERT, and the last and the final topic is P5 model. To begin with, let's get an overview of sequence to sequence models. So in sequence to sequence models, typically we have an input sentence and we try to generate the output sequence. So let's consider the context of machine translation. So this is one example of machine translation. So here we have an input sentence in English and we are supposed to generate the output sentence in French. So in this context, so let's start with the encoder part. So this section is the encoder part, and this part is the decoder. So yeah, so to start with, in encoder, what we have is each input word is the input is sentence is firstly tokenized, and each word is sent one at a time. So we have input one, input two, input three. These are the three words in the input. So yeah, so for each input word, there is a encoder hidden state that is generated. So we pass the input word as an input to the input vector as an input to our RNN, and the RNN generates a encoder hidden state. So this is also a vector. So yeah, so we pass that vector to the next state of the RNN. So in the next state, we have the next input that comes in, and we have another encoder output that is generated. So if we actually, in terms of the intuition, so this encoder hidden state for the second input word, that is supposed to contain the information of all the words that have occurred previously. So here we have one other word, but in general, any encoder hidden state captures the content, the words that have occurred previously. So that's the intuition behind this encoder hidden state. It basically provides the context, the entire context of all the words that have occurred previously. So as we progress, so in the final hidden, the encoder hidden state for the final word which is generated. So this is supposed to contain the representation for the entire sentence. So this is the final hidden state. So it is supposed to capture the information of the entire input sentence. So that is so this is what happens in an encoder. At the encoder, we basically encode the entire sentence in the form of a vector. So that vector is this final encoder hidden state. So once we generate that, let's get started with the decoder portion. So in decoder, what we do is we supply this final encoder hidden state as a initial hidden state vector for the first input. So the first input is a start word. Yeah, so unlike the input where we have three words and we need to generate these output words, we also have these two additional words, start token and end token. So start token acts like the initiation BERT. So that is where that is how the decoder process starts. So this is usually a default vector that is provided, or a zero vector. We start out with that, and the initialization here is done with help of this encoder hidden state. So once we do that, and in the first timestamp, we have a decoder hidden state and that is generated with the help of the decoder RNN. And once this is generated, we use this to generate our first output word. Um, so once again, this is not exactly uh, an output word that is generated. We typically get a probability distribution here. So this decoder hidden state is used to generate a probability distribution over the entire output vocab. So that is the probability, that is what is actually generated. But if we actually want to pick out one word, what we do is we typically take the most probable word out of the probability distribution that is generated here. So that is what we mean by the output word. So although probability distribution is generated on the output vocab, we can pick one particular word, maybe the most probable word that is generated. So that is how we generate the output, the first output word. Now, once we generate the first output word, what we do is we pass on that output word as an input to the next step. So yeah, so we pass on this vector representation, the output, the actual output, like let's say, for example, this word is J, the first one. So in our in our word embeddings, through our word embeddings, we have a representation for J. So that is basically passed here, the vector representation for J that is passed. So this basically generates the word J, but the vector representation for J, that is what is passed here. So once we pass that, and we also have this decoder, the previous decoder hidden state that is provided, and these two are taken as the inputs, and we have the next decoder hidden state, and similarly we generate the next output word. So this process will go on till the point we generate an end token. So as we saw, like let's say for example, this is the end. So here what typically happens is we have a probability distribution. So if the probability distribution for the end word is the highest, let's say, then the end word is the output word that is that we get here. So once we get that output word, we can take it as a signal to stop the decoding process. So that's how it works. Now, in terms of the training of decoder, there's a slight difference between what happens during the training of a decoder and what happens during the inference time. So, so during training, what happens is we have a phenomena called teacher forcing. So, what this basically means is teacher forcing. We actually, so the output word which is generated here, we have an option to pass that word that we have generated in the previous time step, the vector of that word, we can pass on to the next time step. Or one more option that we have, since this is supervised data, we have parallel corpus. So since this is supervised data, we can actually supply the word which is present in our reference. So so this word J, so the vector representation for this word that can be passed here. So yeah, so instead of passing what has been generated here, we can also take uh, the uh, the word from the reference, from the reference sentence. So that is what happens during training. So during training, this helps us do a faster training for the decoder. So that's the benefit of it. This is not followed during inference, obviously, because during inference we don't have such a reference. So what we do is we generate the output word here and then pass on the vector representation for that word for the next timestamp. So that is the process that is there. So this is what is the difference between training and the inference part of the decoder. Encoder, on the other hand, does not have any differences between training and inference. It's exactly the same. Now, once we so we have a overview of the sequence to sequence model. Now coming on to the main topic. So the So we try to understand the intuition behind the attention mechanisms. So this is one example. So we have the sentence "How was your day" in English, and we have to generate this sentence from other shape that's the journey. So forgive me if the pronunciation is incorrect, but yeah. So this is an output sentence in French that we need to generate. So here, any attention mechanism, what it typically does is um, we try to give scores for different input words. So here we have 4 input words. How was your day? So for each output word that we need to generate, we try to assign a score. So for each output word, we try to assign a score for each of the input words. So here we have 4 input words, and we'll have 4 scores here. So each of the scores basically need to sum up to 1. So it's like a probability distribution of scores. So these scores basically indicate how important uh, how the importance of the input words. So to generate the word journey corresponds to this word day in English. So we need to pay more attention to the word day. So this weight is supposed to be higher. So that's what we like this illustration shows. The last word, the word day, has a high score. So like for example, this one is zero point 0.8, and the rest of them is 0.1, and this is 0.05, and this is a 0.05. So the other words, they don't get much importance. Basically, this how was your don't get much importance here, but the word day gets a high score here. So yeah, so that is the goal of our attention mechanism. Any attention mechanism that we have, that should help us um, attend to certain words in the input. So it should be able to make such distinction. So that's the goal. We haven't really talked about how exactly it's done, but this is the overall intuition on what exactly attention means, and what are these attention scores, and what are they computed on. So here they're computed on the input words. So coming to the attention mechanisms in RNNs, so this is one attention mechanism. So this is Bardanow or additive attention mechanism. So here, typically what happens is we have the encoder portion where the input is passed to the encoder, and we have encoder hidden states. Now, unlike the sequence model where only the last encoder hidden state is passed on to the decoder, we collect all the encoder hidden states for each of our inputs. So we correct them here, and we pass them to the decoder. So the decoder uses these encoder hidden states to generate a context vector at each timestamp. So this context vector is generated at each timestamp, and that basically captures the importance that needs to be given to the input word. So for example, when we are generating the first context vector here, should give more importance to the corresponding word. So in the previous example, let's say journée corresponds to day. So the last context vector which is there, that needs to be I mean, this last hidden encoder hidden state that is there, uh, it should be represented it should be representative of this last hidden state. So it should capture this context vector, should capture this, because that is what the correspondence is. So yeah, so we'll once again go through the steps on how to actually compute this context vector. Yeah, once you compute this context vector, we pass that on to the input, and that helps in generating better output words, which yeah. So compared to a mechanism, a plain sequence model where we don't have any attention, this has shown this has given better results. Yeah. So now moving on to the topic on how exactly this context vector is calculated and how it is used. So this is an illustration that shows step by step on how it is computed. So to begin with, so the first step which is there, uh, we have two vectors that are generated here. So this is a matrix actually, but this is a vector. So what this basically represents is we take the decoder hidden state. So for example, let's say we take the first decoder hidden state. So let's say we take this, and what we do is we multiply with a matrix W decoder. So this is a matrix which helps us do a linear transformation of the decoder hidden state, and this is the output of the linear transformation. Similarly, we have the encoder outputs which are there. So there are different vectors. Each of these are different vectors. So yeah, so each of them are vectors. So all of these vectors, these are basically the encoder outputs. So the encoder outputs are multiplied by another matrix W encoder. So this is another form of linear transformation that is happening. So the first linear transformation was on decoder hidden state. So this is on encoder hidden state. So once we do this transformation, we have representation for the encoder output words in a different space. It's a linear transformation. So we are just transforming the space. So once we transform the spaces, what we do is we add them up. So all the so we add the decoder hidden state. So we add that to each of the encoder hidden states. So this is actually so let's say we have two encoder hidden states. So and here we have only one, so we do it one at a time, one decoder hidden state. So we hidden vector. So hidden. So here we actually add this uh, vector onto this vector and this first column, and we get one out. We get another resultant vector. So similarly, we add this vector to this next column, and we have another a new column that we generated. So this is done column wise. So this is sort of a broadcast operation, broadcast addition. So it's not the typical addition that we see. So once we do that, we basically have a representation of that is a combination. This representation is basically a combination of both the encoder hidden vector and the decoder hidden vector. So once we have this representation, we also do the tan h. So that is another part. So we apply tan h to each cell. So yeah, so that is an activation that we apply, a non-linear activation. So once we do that, so once again, if there are two encoder outputs or there are two input words, the output that is generated here will have two input. We'll have two columns here. So similarly, in this example, we had three inputs. So here we'll have a matrix where there are three columns. So yeah, so here we have only two columns, which because we are considering only two input words. So yeah. So once we have that, we actually do another linear transformation, not exactly a linear transformation, but we do a dot product. So we have this W alignment vector. It's a row vector. So we do a dot product. So if we do dot product of this and this column, we get one single scalar. So similarly with this dot product of this with this, we get another scalar. So yeah, so these are the scalars that are generated. So these are called the alignment scores. Yeah. So once these alignment scores are generated, So these scores, since they are typically dot products, they may not be on a scale of 0 to 1, and they may not add up to 1. So that's why we apply a softmax to basically generate scores that are between 0 and 1 also, and also sum up to 1. So these are called attention weights. So yeah, so these attention weights, so what they typically indicate is they for each of the input hidden states that are present. So for each of these hidden states, we assign a score to them. So here we have three, so we assign three scores. But here we are assuming that we have only two inputs, so we have two scores. So they typically indicate how valuable are the input words. So this since we have 0.73 here, this basically shows that the second encoder hidden state is more important. So yeah, it shows the importance. So once we have these importance scores, what we do is we multiply them with the encoder outputs which are there. So we multiply 0.27 with this column, and we multiply 0.73 with this column. So yeah, so we multiply them, and what we do is after multiplication we add them up. So that is another operation. So um, it's like a mixture of all the encoder outputs that we are trying to find. So we once we multiply with the attention scores, we actually add them up to generate this context vector. So context vector is basically um, a linear combination of all our encoder outputs. And what exactly are these, how exactly is the linear combination is done? That is done with the help of these attention weights. So the attention weights are the are multiplied with the encoder outputs, and then the linear addition is done. So that is how the context vector is generated. So this is one way of generating the context vector. As you can see, we have many addition operations. So whatever interactions we have between decoder hidden vector and the encoder hidden vectors, they are in the form of addition. So we added up here, and then we generated the output. So so that's why this attention mechanism is called additive attention mechanism. So yeah, so once we have this context vector, what we do is we add this context vector onto the embedding. So if we look at sequence to sequence models, we don't have this portion, this context vector we don't have. We just pass on the vector representation of the previous word as an input to the next timestamp. So instead of just passing it as it is, what we do is here we add the context vector to the vector that was generated earlier, and then pass that on to the decoder array. So that's the small change that we do. So once we do that, we have a new decoder hidden state that is generated, and from that decoded hidden state, we generate the second output word. So and this goes on. Yeah. So this is one attention mechanism. Similarly, we have other types of attention mechanisms. So this is another form of attention mechanism. So the differences are basically in terms of how the context vector is computed and how is it exactly used. So those are the two main differences between. So here, if you can see, the context vector is also used to generate the output of the first word. It's not just passed on to the next input or added to the next input. It also helps to generate the current word. So that's a small difference that is there. Yeah, and in this attention mechanism, the context vector is calculated differently. So we have different operations to. So previously there was addition. So addition, the encoder hidden state and the decoder hidden state interacted in a additive manner. So here we have other forms of interaction. So we have a dot product alignment scoring function. We have a general one, and we have a concat. one. So typically what this uh, alignment function does is it calculates similarity between encoder and the decoder. So that's our goal actually, to find out um, so we assign a score to each of the encoder vectors. So the score basically represents how relevant the encoder vector is to the decoder vector. So the relevance is basically indicated in one way with the similarity. So that's the reason we have dot product here. So as you know, dot product is the higher the dot product, the more similar the two vectors, the two here the encoder and the decoder. So that's the reason we use dot product. So similarly, the general form, in the general form, it's the same as dot product. It's just that we multiply with this matrix, linear transformation of it. And similarly, we have another concurrent behavior where we add them up. Yeah. So these are different kinds of scoring mechanisms that are there. Yeah. So yeah, so that is the overall idea on how attention mechanism works. What are the two forms of attention? There are several forms of attention, but the underlying idea is similar for all of them. Now, coming to the issues with these recurrent models, so there are two main issues. So the first issue is related to linear interaction distance. So what this basically means is, let's consider one example. So this is an example. There is a dog in the park next to my house, and it has sharp teeth. So here, if you see the word "it," basically refers to the word dog. So yeah, and there are a lot of words in between it and dog. So it's pretty difficult to carry such a dependency of dog to it. Although there are some techniques like LSTMs and GRUs which help us, still it's not possible to capture it. So yeah, so like one of the main reasons this is happening is we have a linear order. So by linear order, I mean we have to go one word at a time. So we have to start from the left and go one word at a time to the right, or we do from right to left. Either ways, we have to go in one word at a time. So that's the linear order which is there. We cannot like skip words or directly connect to words, etc. So this linear order needs to be followed. So that is actually a constraint for us in capturing these dependencies. So it poses problems. So even if we use LSTMs and RNNs, we still see such issues um, in capturing such long-term dependencies. So the next issue is lack of parallelizability. So by parallelizability, we mean that since there is a linear order where we go one word at a time, we cannot actually compute the output of some nth word before calculating the output for n minus 1 words. So yeah, so we have to follow a linear order. Now um, with the introduction of GPUs, etc., the parallel computation is really fast, but we are not able to exploit it because of this linear dependency. We have to go one word at a time. So we are not able to reap the benefits of GPUs. So these are like two main issues for recurrent models. So because of this lack of parallelizability, the training time also increases. So that's another effect. Here are some references to attention modeling. The next topic that we'll be covering is about transformers. So this is how typically a transformer looks from an Uber level. So we have an input sentence, JSV to the end, and we need a output English translation for this. So this is not anything new. We have already covered similar architecture earlier. So we have an encoder which encodes the input and then decoder which generates the output. So there is nothing new exactly new about this. So if you look at a closer view, we see that the encoders are stacked on top of each other. So so encoders are stacked on top of each other, and similarly the decoders as well. in terms of the flow of the inputs and how exactly they flow through this stack of encoders, we see that for each input word. So for example, here we have three input words, J to A to the M. So they are passed on to the first encoder block. So let's say those are passed on to the first encoder block like this. So what the first encoder block does is it generates three vectors representing each of these words. So these three are input vectors, and output vectors are some transform vectors are generated for each of these words. So if we have three input words, we will have three output words. So that's how typically an encoder works. So, so to start with, for example, this word J, we typically use word-to-vec or GLOW word embedding to start this to represent these word vectors. So once we start with these word-to-vec or GLOW such GLOW embeddings, the encoders basically transform these representations to bring new vectors, to generate new vectors for each of these words. So if we pass through this stack of encoders, finally for each input word, we will have an encoded representation for each input word. Now, once we generate those, we pass all of these representations. So in this case, we have three representations, three vectors. So we pass all of them to each of the decoder layers. So that's the kind of flow that is in the data flow that is seen. And the decoder generates the output translation. So the next obvious question would be on how exactly are these transformed representations from each encoder generated. So this picture basically shows the inner details of encoder block and one decoder block. So once again, the goal here in encoder is to generate a transformed representation for each input word. So this transformed representation is mainly generated with the help of this self-attention block within the encoder. So let's have a closer look on what exactly is this self-attention. So here we have two input words, thinking and machines. So these are the two input words. So they are represented by these vectors x1 and x2. So those are the vectors to start with. Now what we have is for each of these input words, we represent them by a query vector. This is the query vector, a key vector, and a value vector. So these vectors, these are obtained by multiplying this input vector x1, for example. We multiply x1 with this WQ, this is a matrix. So we multiply x1 with WQ, and that basically is like a linear transformation of this input vector. So yeah, so so this Q1 is basically obtained by a linear transformation of x1 via this matrix WQ. Similarly, this other set of vectors which are there, a key vector and value vector. So these are generated by multiplying the same input x1 with a different weight matrix. So here we have a key weight matrix and that generates a key vector. So yeah. So these matrices, the query, key, and value matrices, these actually are common. Are basically there is only one single query, key, and value matrix for one block of self-attention. So irrespective of what x1, x2, or what our inputs are, we have a fixed we have these matrices are fixed for this self-attention block. So apart from acting as a mechanism through which linear transformation can be carried out, we can also reduce the dimension. So let's say this x1 is of dimensions. So let's say x1 is of dimensions 512. Now, if our WQ is a matrix of dimensions 512 into 64, let's say. So then what will happen is when we multiply x1 with WQ, the dimension of this Q1 vector is 64. So we are actually reducing the size of the input embedding as well. So we'll actually see the use of reducing we'll actually try to understand why exactly we'll reduce the size, but for now this is one additional benefit. We can also reduce the size. So these query key and value matrices, they basically represent the input in different spaces. So that's what they basically represent. So for example, when we say that this Q1 is obtained from X1, it's like the representation of the input word X1 in the question space. So in the query space. So it's like the, let's say you have all the queries and they form a certain space. So you're transforming your X1 to that space. So that's how, that's what this basically, this intuitively means. One more way to like get an intuition of what exactly are these query key and value matrices is to consider the scenario of a typical database system. So in a database system, let's say we have a database index. So we typically have a primary index, secondary index, etc. So when we pose a query to the database system, the database system uses this database index to help fetch the value or the answer. So if we the mechanism on how exactly this value is retrieved is, if you look closer into it, the database index, such as a primary index, typically contains keys and values. So what we do is, given the user has posed this query, we actually try to see which of the key is relevant to this query. So once we find out the relevant key, what we do is the corresponding value to a value against that key, we retrieve that. So that's how typically a database system works. Similarly, so it's also in a similar way, we can also try to understand the query key and the value matrices. So what we do is we first try to find the relevant key vector for our query vector, right? And then we pull out the associated value vector. So that's how these two can be related, the scenario of database index and the self-attention that we are seeing here. Yeah, so this basically mentions how exactly both are related. So we try to retrieve the values corresponding to a queries with the help of relevant keys. So we try to find the relevant keys for a query and then pull out the associated values from it. So that's the process. So if we try to again look at how it's actually implemented, the self-attention mechanism. So once again, we have two words, thinking and machines. So, and we already saw how this query key and value vectors are generated. So once these are generated, what we do is we take the query vector Q1 for the first word, and we do a dot product of this Q1 with K1. So we do a dot product of these two, and so that is basically this. And we also do a dot product between Q1 and K2. So yeah, this dot product is this. So yeah, so basically what we see is we are doing dot products over all the key vectors which are there for different words. So here we have only two words. So we are doing dot product against two words. If we have n words, we'll have n such dot products. So just as we try to retrieve the closest key to our query in database context, we try to find the closest key vector. So the closest key vector is depicted by this dot product. So dot product indicate the higher the dot product, the closer the two vectors are. So the relevance of the key vector to the query is represented by the dot product. So that's one way in which we can capture the relevance of a key and the query. So yeah, so we try to find the relevant keys for this query. So the score basically indicates the relevance. So the more the score is, the more the relevant is this key to this query. So yeah, so that's the intuition. So once we find out this relevance scores, we also uh, divide by, so at this stage, we also divide by a constant. So this is typically root dimensions of the input. The reason that we do this is um, in case our dot product leads to large values. So here it's 112, but let's say it is pretty large because there is no constraint on whether on what should be the magnitude of these vectors. There's no constraint, so it could be possible that there's a large dot product. So in order to bring it down, we multiply with some constant. So once we do that, we have some scores that are generated. Then what we do is, since these scores are not on a scale of 0 to 1, and also they don't add up to 1, so we use a softmax to get those probability scores. So probability is basically how similar the key is, probability of this key being similar to the query. So that is basically the score, this value that is there. So yeah, so once we compute this similarity scores between for this query Q1 um, with respect to all keys. So we take only one Q1 and then find out the relevance of various keys. So once we do that, we normalize it and then we get this softmax scores. So once we calculate the scores, what we do is, our next step is that we multiply the scores with the value vector. So we once again saw that every word is associated with query key and value vectors. So the value vectors that are present here, this value vectors, we multiply those. We do a scalar product of this value vector with the score. So 0.88 is multiplied with this. Similarly, 0.12 is multiplied with value vector, second value vector. And once we multiply all of them, we actually add them up. So we multiply them and then add them up. So yeah, so that basically gives a representation. A representation in terms of other value vectors for the current word. So once again, we are only dealing with this word x1. So only for q1 and x1, we generated a representation that is like combination of different value vectors, and that combination is decided based on this scores. So this is the contextual representation of the word that we get. So previously we saw that query key and value matrices generate query key and value vectors. And now the query matrix helps in doing a linear transformation to a different space. So let's say this dimension of the initial word is 512, and we transform it into a 64 dimension query vector, value vector, and key vector. So since we have reduced the dimensions, finally when we combine the value vectors, etc., and then generate a contextual representation for this word, for each of the words, they will be of dimension 64 because we have reduced the dimension through this matrices. So since we have reduced the dimensions, there's a concept called multi-head attention, where what we do is we generate several such 64 dimensional contextual representations for every input word, and then we concatenate them. So let's say you concatenate two vectors of 64 dimensions, you get a combined vector of size 128. So similarly, if you concatenate eight such uh, vectors, you will get a contextual embedding that is of size 512. So yeah, so 64 into 8, that gives that is actually 512. So yeah, so that is basically the dimensionality of the input word. So yeah, so we are able to so for each such 64 dimension, there is an associated query key and value matrices. So we'll have 8 such query key and value matrices. So yeah, so each query key and value matrix is called a head. So we have several such heads. So that's the reason it's called multi-head attention. Now coming to positional embedding. So the self-attention that we saw earlier, in itself, it does not depend on the order of words. So in the previous slides, when we actually saw how this self-attention is computed, we haven't actually noticed any operation that depends on the position of the words. It's just dot products and multiplications, etc. So yeah, so we introduce a concept called positional embedding that helps us to introduce this position variable. So yeah, to account for the position of words. There are different ways in which position embedding vectors are derived. So yeah, so what this position embedding does is for the input representation for x1, let's say, we add the position embedding corresponding to the position at which x1 is present. So here x1 is present at the first position. So there is a fixed position embedding t1. So it does not depend on actually what word is present at the first position. Irrespective of what x1 is, what word is x1, it just there is a vector, there's a fixed vector corresponding to this position that is added up to x1, and then that generates that is added up, and there is a new vector that is generated. So this vector is supplied to the, or is provided to the encoder. So that's how it typically works. Now there are different ways in which these position embedding vectors at each position are fixed or derived. So there's a concept called sinusoidal position representation. So that basically gives a fixed representation at each position. We also have learnable position representations. So those are also used. They have their own advantages and disadvantages. Now, so this covers the encoder portion. So we basically saw how exactly self-attention is calculated and how exactly is the contextual representation generated. So yeah, once this contextual representation is generated, we also have one more additional layer that is present. So there is a residual connection. So residual connection typically means that we we have a connection between the output of a previous layer to the output of the next layer. So there's a direct connection, so that the gradient propagation happens easily. So we typically see them in several other networks. Similarly, we also see a residual connection here. Um, so we don't actually directly. So earlier we saw that once the self attention is done, there is a feed forward network. Uh, but we don't actually pass it directly to the feed forward network. What we do is we have a layer normalization layer in between, which basically normalizes the contextual representation for each words. So it first calculates the addition between the contextual representation and the original input x1. So z1 plus x1, there is some new vector that is generated. Similarly, z2 plus x2, there's a new vector. So we have, this is like the matrix version of the addition operation. So once we do this addition part, we do a normalization of all these vectors. So we have, let's say we have 4 input words. Here we have 2 input words, but let's say we have 4 input words, we'll have 4 contextual representations. So once we have those 4 contextual representations, we normalize them and do the normalization and get a normalized vector. So those normalized vectors are passed on to the feed forward. So that's the process. So there's a layer norm or layer normalization layer in between. We don't directly pass it to the feed forward network. So yeah, once we pass to the feed forward network, the output of feed forward network is once again added to the this Z1 is added to this output, to whatever output comes here. The Z1 is added here, and similarly Z2 is added to that, and we also normalize that. So once this entire process completes, the output representations that are generated here, they are passed on to the next encoder block. So this is the first encoder. So yeah, so we have several such encoders stacked on top of each other. So that completes the encoder part of the transform model. Encoder helps in transforming the input words to contextual representations of those words. Now let's proceed to the decoder part. So the encoder outputs that were produced earlier, those are supplied, those are supplied to the decoder blocks as well. So decoder typically contains 2 main components. So this is one component, encoder decoder attention, and the other important component is self attention. So the self attention that we see here is similar to what we have seen earlier in the encoder model, except for the fact that in the decoder, the words are generated one word at a time. So we don't have we cannot use the entire output reference sentence that we have and generate the self attention. So that is not possible because in decoder, we typically generate one word at a time. So first we, let's say this is a decoder. We start out with the start word, and then we generate one word, W1, and that is passed as the input to the passed as the input, and we have W2. So this is the usual process in which the decoder works. So we cannot actually use the reference words that we have. We obviously we know the entire output sentence. So we have the output transliteration. We have these words, but we cannot use them to conduct self-intention. So for example, let's say we are conducting self-attention at second word. We cannot use the third, fourth, fifth words, etc. We can only use the words prior to the second word. So yeah, so that's one aspect in which the self-attention in the decoder is different from what we have seen in encoder. So to ensure that we don't calculate the scores for the future words, or in other words, we assign a score of 0. What we do is we have a process called masking. masking of future words, where we assign a score value of -infinity to all the future words. So since we assign -infinity, in the process of softmax, what will happen is the scores associated to all the future words turn out to be 0, because typically uh, in a softmax, what we do is we do e power, let's say x1 by e power x2 x1 plus um, e power x2 and so on. So let's say something is -infinity. So this one turns out to be 1. So sorry, this one turns out to be 0. So that way it's not adding any score to the computation, to the score computation. So yeah, so that's what is typically done to ensure that we don't use the future names. Now, apart from this self-attention module, the other important module is encoder-decoder attention. It's similar to the self-attention that we saw earlier, but except for the fact that the encoder-decoder is multi-head attention, where the queries the queries are the query vectors which are present. Those are with respect to the decoder words. So yeah, the query vectors are with respect to decoder words, and the key and value matrices, um, and the vectors, the key and value vectors which are there, those come from the encoder. So the earlier encoder outputs which were generated, we multiply them with certain key and value matrices to generate the keys and values for these encoder outputs. Now, once you generate the keys and values, those keys and values are um, are used to calculate this encoder decoder attention. So previously, to calculate self-attention, in the self-attention block, we have all the key value and um, vectors for each word in our input. Here we don't do that. We have the query vectors only for the decoder words, and the key and value vectors are from the encoder outputs. So because we want to like we want to find a linear combination of the encoder vectors and represent and find out a contextual representation for the decoder words. So since the interaction is between encoder and decoder, that's the process that we carry out. So here are some references for transformers. So that completes the transformer model. Now let's move on to the next topic, which is subword modeling. The traditional models that we have used till now, they typically do the tokenization in the form of words. So each word is taken as a separate token, but there are some problems associated with doing that. So that's because any new word or a small variation of that word, of an existing word in the vocabulary, is treated as unknown. And also, the if you want to cover all the words that are there, let's say we have some languages such as Swahili, etc., which have complex morphology. So we can combine certain words, or different prefixes, suffixes can be appended to words. So if we if we want to consider all words in the vocabulary, that vocabulary will be extremely large. So we cannot actually uh, it's not feasible to consider such a large vocabulary. So that's another issue. If you want to actually consider these variations into picture and expand our vocabulary, that's not possible. And if you don't expand our vocabulary, we tend to have a lot of unknown values. So that is again not very useful. So to deal with these problems, we have an approach called subword modeling. So where the learning is conducted on the parts of the words or the subwords. So here is one example where the word unfortunately is divided into around 5 parts. So there are several ways to do subword modeling. One of the popular ways is byte for encoding. So here what we do is, this is based on information theory principle on finding out the least number of tokens to represent a text data set. So here what we do is we initialize the vocabulary with single characters. So we with single characters we initialize them. Then what we do is we try to represent each word in the corpus. So that is, the vocabulary is consists of single words. Now all the words that exist in the corpus or the text data that we have, we represent it as a combination of these characters along with a special end token of word. So yeah, so for example, let's say you have a word called y. Sorry, let's say you have a word called y. So what we do is we represent this y word in terms of the characters or the subwords which we have in vocabulary. So initially, to start with, since our vocabulary contains only characters, we have the word y is considered as w, h, y, and there is also so along with y we also append a like a end token. So it indicates that this y occurs in the end. So there's this helps us in differentiating with the y that occurs in between the sentence or in the suffix with respect to y that occurs in the end. So this is how we divide. So once we do this, we count the number of character pairs that have come in. So let's say here w in why is one word. So there are different pairs of words here. So wh can be treated as one pair and hy can be treated as another pair. So we count all these um, all such two word pairs, two character pairs, and once we count them, what we do is we find the most frequent pair and add that pair as part of the vocabulary. So yeah, so once we do that, we successfully repeat this process, finding the most frequent pair in each iteration and adding that back to vocabulary. So that's the overall idea of byte pair encoding. So there are other forms of subword embeddings like unigram subword tokenization. This unigram subword tokenization, it helps us prevent some of the issues that are present in the byte pair encoding. Because byte pair encoding, it can have multiple encodings for the same word, multiple valid encodings. So in order to prevent that, we introduce a concept called likelihood of pairs, etc. So yeah, so this is unigram subword tokenization. Similarly, we have word piece tokenization, which uses likelihood rather than count frequency to merge words. Yeah, we also have a sentence piece. So yeah, so there are different types of subword modeling techniques that are there. Okay, so so that's typically how the tokenization is conducted. We no longer use word level tokenization. We use subword tokens because there are several benefits associated with them. Now let's move on to another concept. So we try to understand how pre-training is conducted in various settings. So previously we have seen that the transformer model has encoder, and there's an encoder part and there is a decoder. The output of encoder is given to a decoder and it generates an output. So we have an input and there is an encoder and we have a decoder here. So in the original setting of transformer, there was no pre-training done. It was only supplied with parallel corpus and the self-attention, etc. was done from scratch. So yeah, there was no pre-training. So now we try to understand if it's how exactly do we do the pre-training of these different parts of the transformer model. So how do we do the pre-training for encoder? How do you do pre-training for decoder? And would it be possible to do a pre-training for both encoder and decoder at a time? So we'll try to look at these various scenarios. Firstly, let's try to understand how to exactly pre-train the decoder part. So pre-training in general that we have seen in LSTMs, etc., was typically conducted via a language modeling task. So in this task, every word is supposed to predict the immediate next word. So this is a sentence, for example. Now this first word is supposed to predict the second word. So that's why the second word is present, is supplied in the output. So that's the typical process of how the pre-training is conducted using a language modeling objective or language modeling setup. So we use such kind of pre-training for a decoder. So the transformer decoder that we saw earlier, we can use such a form of pre-training for the transformer decoder. Now, in general, just to emphasize once again, decoder is typically a model which takes an input word. So, for example, it takes this input word uh, and it takes information from all the words till this input word and then generates an output word. So that's the typical process of a decoder. So decoder will not be able to see the future words. So these words which are there, it won't be able to see. So only the previous words can be used by a decoder. This is unlike the encoder. In encoder, bidirectional attention is possible. You can get information from any of the words in your sentence, but that is not possible for a decoder. So yeah, so this is an important distinction and an important difference in the pre-training approaches between encoder and decoder. So this is a pre-training approach for decoder. Basically, we use the language modeling objective and try to predict the next word. Now, when we try to pre-train a transformer decoder, we obtain this model called generative pre-trained transformer. So this is a GPT model. So GPT model has it's a big model, so it contains around 12 layers and 40,000 BP codes, etc. And it's trained on book corpus. So the pre-training takes a couple of days to conduct. And yeah, and as mentioned before, it is conducted via language modeling objective. So once the pre-training is conducted, the GPT model can be used for fine-tuning tasks. So let's say your fine-tuning task is a sentence classification, which basically means you need to predict a certain class for your input. So in that case, what you do is you take the last words outputs and then connect a linear layer and try to generate the class from it. So that's typically the process and how you use pre-trained GPT for sentence classification. If you want to use the pre-trained GPT for sequence prediction itself, then that will be similar to what we have done in the pre-training itself. So in pre-training also we have an input sentence and we try to predict an output sentence. Similarly, when you are doing the fine-tuning on sequence prediction task, it will be a similar procedure. So yeah, so on with the help of this fine tuning on GPT models, there so good results were achieved on 6 out of 8 blue tasks. So these are the results, and this model, which is the pre-trained GPT model. Now let's move on to another form of pre-training, which is BERT. So BERT is pre-training an encoder. So encoder is a transformer formulation in which bidirectional context can be incorporated. So yeah, so it's different from a decoder in that way. Yeah. So once again, so there is a reason why language modeling cannot be used for as a pre-training objective for encoder, because typically in bidirectional settings, when we try to use language modeling, we tend to predict the input and the output words seem to be there will be a stage where both of them would be the same. So that's the reason language modeling cannot be used in a bidirectional context setting. So we use a different form of pre-training approach for pre-training the encoder, which is basically the masked language modeling. So in this, what we do is we replace some words in the input sentence with uh, masks. So we replace them with mask tokens, and then we pass the entire sentence to the encoder, and then try to predict the mask tokens. So that is the typical objective in and how we conduct pre-training for encoder. So when BERT was released, there were two forms of BERT. One is BERT large and one is BERT small. And BERT large is basically a bigger model. And apart from that, there are some specifics on how this masking is exactly done. So around 15% of the words are masked. So even within masking, only 80% are masked, and 10% are left as it is, and 10% are replaced by random token. So there are small variations on how this is done. The main objective is, let's say, you mask for certain words, and you don't actually retain the original words, then maybe the model will lose track of what is the actual original word. So that's the reason you sometimes mask, you retain, and other times you retain the original word, etc. So another task in which BERT is trained is also next sentence prediction. So here, what we do is, given two sentences, the model predicts whether the sentences are successive or they are randomly chosen from different places. So yeah, once again, BERT, when it was released, it showed state-of-the-art performance on all the glue tasks. So it beat the other models. Here are some references for BERT. Now coming to our last section, it's about the T5 model. So T5 model is basically a model that a pre-training approach that pre-trains both the encoder and the decoder. So typically, uh, so let's consider how exactly this is done. So in general, whenever we are doing fine tuning on these pre-trained models, we fine tune on one task at a time. So in the T5 model, what they suggest is, instead of fine tuning on one task at a time, you do the learning at a time for all the models. To achieve this, they propose a formulation where we have same loss function, same hyperparameters on LM3 task. The way they do that is, both the input and the output are treated as strings. So let's say we have this use case where the output needs to be a real number. Still, even if it's a real number, what do is we treat it as a string and then try to predict it. So if it's a real number, we convert it to a string. If it's a class, we convert it to a string. If it is actually a sentence, that is anyways in the form of a string. So this is the formulation in which T5 model is built. So there is small variation in how the input is given to the model. We don't actually supply the input as it is. We actually mention the task on which the input is supposed to be trained on. So here it's translation task, so we put a word translate. So here it's the task, it's a cola task, so we put the cola word in the beginning. Similarly, this is summarization where, so we put summarize. So these are small nitty-gritty details on how exactly it's done. So the main aspect regarding this T5 model is that pre-training is done both on encoder and decoder. So the procedure of pre-training is through corrupting spans or denoising mechanism. So this is the denoising mechanism, where what we actually do is, given a sentence, we replace a span of tokens um, with certain markers like X, Y, etc. And so this is what is provided in the encoder. And what we try to predict in the decoder is this. So we try to predict the words that are missing, and other words need to be left um, as blanks. So that's what we do in the decoder. So this is a diagram on how it's done. So for example, President Franklin, M born M January 1882. So these M needs to be predicted uh, in the decoder. So what we do is, M is actually D Roosevelt was. So that is actually what is M here. And the other M which is missing is actually in. So the ones that we need to predict, that we present it to the decoder. So that's the pre-training process. And we also have a fine-tuning step for T5 model. In conclusion, we have discussed on various topics related to attention and self-attention. We have also seen how these concepts are applied to transformers, BERT, T5, and other pre-trained models. So pre-training is the important aspect that or takeaway from this tutorial. We have seen that when we pre-train the models, we have good improvements on the downstream tasks. We have seen the same results in Alexa as well, where we use such pre-trained models and then fine-tune on customer-facing tasks like intent prediction, NER, etc. So in Alexa, when a user says play song from X, so we have to identify the intent behind this utterance, the intent the user is trying to play a song. So detecting such intents, etc. We do it over pre-trained models. So in Alexa, we not just have one language, we have several languages. Alexa supports several European languages. So the pre-trained models that we use um, tend to be across different languages, across multiple languages, etc. So yeah, thank you everyone. I hope you found this presentation useful.